want to talk about my approach for searching for extraterrestrial microbes, because as everybody in this audience knows, we're not looking for little green men and women. We're looking for microbes. That's the most likely kind of life we would find on another planet or world. And there are basically three different approaches for searching for extraterrestrial microbes, two of which are extremely popular. One was using defining criteria for life based on a privileged definition of life. That's still very popular. I've worked very hard to convince people it's a mistake, and I'll briefly explain why it's a mistake, or just highlight why it's a mistake, and urge you to read some of my papers if you aren't convinced. And then there's an appeal to a preliminary universal theory of life. And this is implicit in the selection of so-called agnostic criteria for life. It's very odd they use the word agnostic, which means suspending judgment. And then they treat them as necessary conditions for life. And in some cases, they make this very explicit and call them necessary conditions for life. This is really the same as a partial definition for life. So it really doesn't get us any further than the problems that we had with defining criteria for life. But then if neither of these work, which I have argued they don't, the question is, what will work? My proposal is that you use tentative criteria to search for potentially biological anomalies. And the potentially biological anomalies should be highlighted in blue here, because that's what I'm going to be spending most of my time talking about. And I don't have much time to develop any of this, but I think I'll try to at least motivate it. So let's see if I can get it to change. Okay. So I just want to quickly, I'm going to go really rapidly. What's wrong with definitions? Well, definitions are about meaning and concepts. They specify no necessary and sufficient conditions for the application of a word, the word being defined, and they can't go beyond human concepts and tell us about things in a mind-independent world. Good example is the classic one that's used in introductions to philosophy of science, introductory logic courses, and that is bachelor. Notice a single quote. That means we're talking about a word, not the thing the word refers to. Means unmarried human male. It doesn't talk about bachelors per se, the things that the word bachelor refers to. It explains what that word happens to mean in English. And the point is that definitions can't go beyond our current concepts of life, which are rooted in biology as familiar life here on Earth, and tell us about the possibilities for life wherever and whenever it may be found in the universe. So what about current biological theory? Well, you might think the amazing morphological diversity of Earth life suggests that all the possibilities for life are represented on Earth today. But as everybody in this audience knows, we now have discovered that's just not true. All life on Earth is just from the bacterium to trees to elephants, all those things we saw here, shares a microbial last universal common ancestor, affectionately dubbed LUCA, and hence represents a single example of life. And we know that life could be at least modestly different at the molecular level, and we don't know how different. Biochemists have constructed non-standard nucleic acids, non-standard proteins using alternative genetic codes to code for the non-standard amino acids. They've also synthesized non-standard nucleic acids from non-standard nucleobases. And this is all kind of the approach, which is you take apart a car and then you put together using parts that are modeled on the original parts, but maybe made of plastic instead of metal, etc. In other words, what we're doing here in deconstructing our form of life and trying to make slight differences is we are synthesizing something that's only modestly different. We just don't know how different life could be from life as we know it on Earth. So there's a dilemma here. How can we recognize truly novel forms of life, examples of life as we don't know it, if we don't have a definition or universal theory of life? Well, I have a proposal of a way to solve that dilemma, which is, well, let me just say, it's not obvious that we'll recognize it if we see it, and especially if it's microbial. My proposal is that we explicitly search for potentially, and the word potentially is really important here. Because just because you find something, which is a potentially biological anomaly, doesn't mean it is a novel form of life. It's a candidate only for that. So the idea here is you explicitly search for potentially biological anomalies as opposed to life per se, which is what you do with the other approaches, defining criteria or agnostic biosignatures, using tentative versus defining criteria for life. Now, I don't have time to go into what tentative criteria consist in, but I just want to note that they would include both characteristics that are universal to Earth life, but might not be universal to life found somewhere else. They might reflect chemical and physical contingencies at the time that life originated on Earth, and their universality might be contingent on those characteristics. And they would also include adaptive environmental characteristics of life as we know it that might be adaptive, say, on an arid climate like Mars. So that's all I can say about it here. But I want to focus on the potentially biological anomalies in the rest of this talk, not the tentative criteria. So potentially biological anomalies are physical systems that resist classification as life or non-life because they violate our Earth-centric biological preconceptions about life. And it's important to see that recognizing a potentially biological anomaly is not something that you can come up with an algorithm for. Why? Because they're unexpected, and an algorithm is not going to tell you about what is unexpected. And I could go on about why a Bayesian approach won't work. I don't have time, but it's important to see that we're looking for something that, gee, what's that? It shouldn't be here. It has characteristics that are suggestive of life, but also characteristics that are suggestive of non-life. And these are cases that kind of straddle the boundary between our current concept of life and non-life. So I think it's important to think about them as only potentially biological, because we might discover they aren't biological. And tentative criteria for life, as I just mentioned, include both allegedly fundamental and non-fundamental characteristics of familiar life, as well as what characteristics are contingent on particular environments in which life has adapted to on Earth. But the advantage here is you don't have to make a decision about, is life the fundamental, most basic characteristic of life, reproduction, genetic-based reproduction or metabolism. On this view, you'd look at both. You would go with a suite of criteria. So I want to just kind of wrap this up by saying, in essence, there are two strategies for searching for extraterrestrial life. You can search under the street light, like searching for your keys under a street light, like ours. You design equipment and methods, agnostic biosignatures, defining criteria for specific kinds of acceptable, under our current understanding, deviations from familiar life. Or you can search for potentially biological anomalies, physical chemical systems that resemble familiar life in provocative ways, and yet also differ from it in unanticipated ways. And I want to end by just pointing out that we have actually run into some potentially biological anomalies. I'm going to give you 3 cases. And many of you will go, oh, no, that's not life. But that's not the point. The point here is that they are anomalies. They are anomalies. The results of the Viking mission labeled release experiment, I've written extensively about this, and I don't believe that perchlorate solves it, because perchlorate explains, since it's only reactive at very high temperatures, why the GCMS that was included didn't find any organic molecules, which, by the way, was the reason that NASA rejected the very anomalous results of the label release experiment as not due to life. It was the results of the GCMS, which were definitive here for NASA. And yet that's what perchlorate explained, but it doesn't explain the results that were in the chamber, because the chamber was only at 10 degrees Celsius, far too low for perchlorate to become reactive. And yes, people have come up with various exotic explanations of how light, sunlight affecting perchlorate, ultraviolet radiation affecting perchlorate could have basically produced more reactive chemicals in the Martian soil. This is a very typical way in which people respond to anomalies. And I think it slows down scientific discovery. I'm not saying that the Viking missions found life. I am saying they found a potentially biological anomaly. Another example that people no longer take very seriously is the bacterial shaped structures in chains of magnetite found in the Allen Hills meteorite. Now, I'm not saying that they found, fossilized Martian life. And I, by the way, haven't kept up with this case, so it may have been satisfactorily explained in terms of, current understanding of geochemistry. I don't know the answer to that, but certainly when it was first discovered, it was a potentially biological anomaly because these were kinds of structures that you wouldn't expect in a meteorite, and they are suggestive of life. Magnetotactic bacteria form chains of magnetite that are remarkably suggestively similar to what was found in the Allen Hills meteorite. The picture on the left is an electron microscopic picture of those structures from a slice of it, and the picture on the left, right, of course, is the meteorite. Finally, I want to talk about, just briefly mention the presence of phosphine gas in the atmosphere of Venus, which is recently discovered and has led to an enormous amount of discussion. And Paul Reimer and I are actually working on a paper on this. I'm very excited about that. I'm not going to say very much more about this because I bet Paul has said something about it to everybody. But the important thing here is that phosphine gas in the atmosphere of Venus is a potentially biological anomaly. It's very hard to explain how you could produce that gas other than via microbes. Now, maybe you can. Maybe there are chemical ways of doing this in an atmosphere like Venus's, and that would explain it. But the important point is that it is a potentially biological anomaly. And I want to close with a final, shall we say, comment. The key to finding truly novel forms of life is to identify potentially biological anomalies. But as the history of anomalies in science, an example would be the precession of perihelion of Mercury, illustrates, and I don't have time to go in, I have tons of cases of these from the history of science. The philosopher Michael Dietrichs and I are actually putting together a book proposal for a book with chapters by different authors on anomalies in science. And that's my big project, and I'm going to be writing, I'm trying to analyze basically, cases from history and look at what they could tell us about current cases. But anyhow, the point is, the history of science, it is difficult to get scientists to take the anomalousness of a phenomenon serious enough to identify it as truly anomalous. That's the first stage. You have to be able to say, okay, we've tried to explain this in the usual ways. It's a genuine anomaly. That doesn't mean that it's going to overthrow our current concepts of physics or chemistry or biology. It means that it should be taken seriously as a challenge to those concepts. The usual approach, however, and what history shows, is to insist upon fitting the anomaly into the current theoretical framework with increasingly implausible conjectures. And my favorite example, that's why I picked the precession of the perihelion of Mercury, is that when they couldn't find it between Mercury and this planet Vulcan, which was hypothesized between basically Mercury and the Sun, some people postulated, well, maybe it has this really weird orbit where the Sun is always between Vulcan and the Earth, so you can't see it from Earth. And then there were other implausible hypotheses, such as the Sun's mass is not homogeneous. Maybe it isn't. Nobody knew at the time. And so it drags Mercury's orbit in this weird way. And this is typical. I have many, many cases. I am actually going to be writing a single-authored book on this. But I think that the work I'm doing has great significance for searching for extraterrestrial life. I would like to change the way we do it. And that's the end.
So I really like this framework because I think it gets to the heart of a lot of the issues we have in thinking about hunting for life. The kind of counter challenge from the theorists who prefer abiotic mechanisms is that life is such a unlikely thing that you need to extensively search for any possible abiotic mechanism and go through all of those before you can discount it. So how do you approach it when, for example, I mean, the example I had in my head was another example, methane on Mars. There was sort of many theoretical papers came out shortly after those detections arguing for abiotic ways to explain it. And they may be stretching things in some ways, but one can always argue that life is perhaps more implausible. So how do you kind of counter the theorists who would argue you should always exhaust all abiotic mechanisms first?
So methane's that's an excellent example. It's surprising how many potentially biological anomalies we've run into, I think. No, you don't. That's the whole point. And that's what they did with Mercury. They made effort after effort to reconcile the deviant orbit of Mercury with Newton's theory of gravity and motion. And they didn't take seriously investigating it as potentially a challenge to that theory. And another example, I think, would be my favorite one, the Viking labeled release experiment. People just kept coming up with explanations that were abiotic to explain how you got those weird chemical reactions in the experiment. They went from exotic states of iron, hydrogen peroxide, superoxides, and finally, oh yeah, perchlorate does it. The emphasis was on explaining it abiotically. And I find the deepest of ironies is the reason NASA went for the abiotic explanation was the results of the GCMS, which the discovery of perchlorate can explain, but it can't explain the results in the actual, labeled release experiment itself. And so what I think is really interesting here is that you need to, at a certain stage, explore the possibility of abiotic explanation, but also explore the possibility of the alternative. Don't get fixated on it's got to be abiotic, because it's not just like our form of life, which is what happened with the labeled release experiment, when 30% of the gas was reabsorbed when they gave it a second helping of the nutrient solution, and no new radioactively labeled gas was emitted. That's very anomalous, and it should have made people think, well, maybe we ought to think, or maybe we ought to go to Mars with equipment that would be able to make those kind of discriminations. I hope that answers your question.